All right, and welcome back. It is time for round 2 of test review for chapter 5. So I apologize if the audio is not fantastic using the built-in microphone on this laptop, which I've never used before. So we're going to get started. We've got a couple more problems. Remember, your test is tomorrow, so make sure to look over all the problems that we've done before, and let's get started. So this was a homework problem, exercise 19 from chapter 5. It says, Mr. Ames is dragging a box full of books from his office to his car. The box and books together have a combined weight of 134 newtons. If the coefficient of static friction between the pavement and the box is 0.55, how hard must Mr. Ames push horizontally on the box in order to start it moving? So what we really need to do is we need to start by making a Freebody diagram. So our givens, and I need to switch my pen, should look like this. This is my Freebody diagram. I have the weight pushing down of 134 newtons. This box isn't falling through the ground. That means there must be some supporting force from the surface going up. This is our normal force. We can see that the one going down has to equal the one going up. Otherwise, we'd be either falling through the surface or we'd be flying up off the ground. So that means that the normal force in this case is going to be 134 newtons. Okay, so now we're going to be pushing. Mr. Ames is going to push on the box, and something's going to be pushing back, because if he's pushing but the box isn't moving because it's going to start moving, that means there has to be a friction force going the other way. Force, friction. Okay, our unknown is this force of friction. And in this case, we have the equation for the force of friction is equal to mu times Fn. And then we'll use Newton's second law, F net is equal to ma to solve. Alright, so I forgot to write down a couple givens. One, they gave us the mu. The mu is equal to 0.55. And then, of course, it says that the box is not yet moving, so that means the acceleration sure must be 0. A equals 0. Alright, so let's go ahead and solve. We got force of friction equals, the mu is 0.55, and Fn is 134. Go over to our handy dandy calculator. 0.5 times 134, and we get this lovely number, 73.7. 73.7 newtons. Alright, so we got that. Now we go into our second equation, F net. Remember, F net comes from the free body diagram. We already said that this and that canceled out. So all that's left is our left force and our right force. So it's going to be negative force of friction plus the pushing force is equal to the object's mass times the acceleration, which was 0. Now, we could figure out what the mass is from the weight, but if you look over here, since it's multiplied times 0, don't really need it. We'll have 0 on this side equals negative 73.7 plus our pushing force. Add the 73.7 to the opposite side. And then we'll get that the force that he is pushing with is 73.7 newtons. Okay, so in this problem, it didn't say what direction we're going. So what we can always just say for this is horizontally. That means he could have been pushing it forward, backwards, left, or right, but he couldn't be pushing it up into the air. Alright, so that's a good little example, quick friction problem. Let's go to the next one. It says Thomas sits on a small rug on a polished wooden floor. If the coefficient of kinetic friction between the rug and the slippery wooden floor is only 0.12, if Thomas weighs 650 newtons, what horizontal force is needed to pull the rug and Thomas across the floor at a constant speed? Anytime we see constant speed, we need to remember that one of our givens is going to be that A is equal to 0. It says that the coefficient of friction is 0.12, so that's mu equals 0.12. Alright, so again, always with the drawing the free body diagram, it says a weight of 650 newtons. It goes straight down. And then it says that he's pushing horizontally. Okay, so now I need to finish up my free body diagram. If his weight is pulling down, but he's not going through the floor, that means there must be some force from the floor that's balancing his weight. We call that the normal force. So straight up opposing the weight, that's Fn. We have a constant speed. Our acceleration is 0. That means that we're not changing our speed. So if I'm pushing to that side and I'm not changing my speed, Newton's first law says that I have to have a balanced force. So this is the force of friction. So our unknown, it says, what is that horizontal force? You should see that this is set up just like the previous problem. You have force of friction is equal to mu times Fn. Then you have F net is equal to ma. So force of friction, we're solving here. Force of friction is equal to mu, which is 0.12, times the Fn, which is going to be 650 newtons. I forgot to label that earlier when I told you that it had to be balanced going straight up, but that's what it is. So now I come back over to the calculator, 650 times 0.12. And we get 78. Equals 78 newtons. And predictably, when we do F net equals ma, again, this part canceled with that part. The force of friction is going to the left. The push I drew to the right, so I put a positive, equals the mass, which I don't know, but the acceleration is 0. So it really doesn't matter. So I add the force of friction again to both sides. And what we come up with is that the force of friction is equal to 78 newtons. And which way are we pushing? Did it give us any directions? Sure didn't. So again, we're pushing this horizontally across the floor. Alright, so 2 problems down. Let's see if we can get a little bit more complicated. And we did. Alright, so we got a lot of things going on here. Now we're going to have an acceleration, which means that we can't run off of our lovely assumption that the acceleration was 0 and F net is equal to 0. So everything's not going to balance out anymore. So what we have to do, we have this 1.4 kilogram block. We should know that kilograms is going to be our keyword for mass. So that means my given, I'm going to start by writing mass is 1.4 kilograms. Okay, it says a rough surface such that the block slows down with an acceleration of negative 1.25 meters per second squared. Means our acceleration is equal to 1.25 with a negative meters per second squared. What is the coefficient of kinetic friction between the block and the surface? So our unknown is our mu. Alright, so let's draw our free body diagram. Going straight down, we have the force of gravity, and Fg is going to be equal to m times g equals 1.4 times 9.8. So 1.4 times 9.8. Come over here, we go 1.4 times 9.8. Enter. That's 13.72. Alright, so we got 13.72. That's my force of gravity. Now, it's sliding freely across a rough surface, but it isn't falling through the ground. And it isn't jumping up in the air, so we have to have that balanced force in the y direction. So my Fn is going to be exactly the same as my Fg in this case. So Fn is 13.72. Alright, so as we come through here, it's slowing down with a negative acceleration. That means I'm going to go ahead and draw my frictional force in the negative direction. So that's negative force of friction. Okay. Alright, so equations. We have the force of friction is equal to mu times Fn. That's the force of friction, use the coefficient of friction times the normal force. Okay. And then we're looking for another piece with this acceleration. That's F net is equal to ma. Alright, so if I look at the first equation, I don't know force of friction yet, and I don't know mu yet, so I'm out of luck on solving that one. If I do F net equals ma, I can solve this problem. So let's plug it in. Again, the y components canceled themselves out. All I'm left with is the force of friction for my net force. And remember, the net force always comes from our free body diagram. That's why if we're going to use Newton's second law, we have to draw a free body diagram. So F net is just going to be negative force of friction because it's going to the left. It is equal to this object's mass, which is 1.4 kilograms, times the object's acceleration, which is negative 1.25 meters per second squared. I guess I really didn't need to write the meters per second squared, but I did. And now I can't stop myself. So enjoy that little mistake. Alright, so on my calculator, multiply 1.4 times negative 1.25. I get negative 1.75. So my negative force of friction is equal to negative 1.75. Alright, look here. My negatives cancel, and now I have force of friction is 1.75 newtons. I wasn't looking for force of friction. What I'm looking for is mu, so I got to keep going. So I have 1.75 equals mu times my normal force, which was 13.72. The 13.72 is multiplying times the mu, so I need to divide by 13.72. Now I guess mu is equal to, well, go back to the calculator, 1.75 divided by 13.72. Get 0.12755. Check my sig figs. believe I've got only 2 right here for the 1.4 kilograms. So I need to round that to 2 sig figs. The 1 is significant, the 2 is significant. The 7 makes the 2 round up, so mu is 0.13. Alright, so some of you might have been wondering, you were looking at the calculator like, well, but there's a negative there. That's because I didn't write in this part without a negative. Mu cannot be a negative number, it has to be a positive. And then the other fantastic question that should be arising in your head sometimes is, what is the unit for mu? The answer is there isn't one. No unit. Also, no direction. It's just a coefficient. Just like in math, a coefficient is just a number. So 0.13 is our answer. We're ready to move on. We are rocking it today. Alright, Ryan and Becca are moving a folding table out of the sunlight. A cup of lemonade with a mass of 0.44 kilograms is on the table. Becca lifts her end of the table before Ryan does, and as a result, the table makes an angle of 15 degrees with the horizontal. Find the components of the cup's weight that are parallel and perpendicular to the plane of the table. Alright, so this is a little bit of a different problem. So I'm going to go ahead and write the givens that we have. We have mass is equal to 0.44 kilograms. And we have our angle is going to be not theta, but phi. It's 15.0 degrees. So I'm going to draw this picture. And it's the same picture that we use for most of these problems. We're going to have a horizontal. Okay, that's pretty close to horizontal. And we're going to have, okay, that didn't work. We're going to actually use the line tool, I guess. So I have a horizontal thing at the bottom, and then I have a ramp. Oh yeah, that's way better. Okay, on my ramp, I have to have my object going straight down is FG. Coming straight out at 90 degrees is going to be FN. Then I have the component that's going to be in the perpendicular side, coming out right here, and the component that's going to be in the parallel side, going right here. This should be at a right angle. My drawing is still slightly off. This should be perpendicular to the surface, parallel to the surface. Alright, so what we've been calling these is, this is FGY, this is FGX, this was, of course, was FG, and this was the normal force. Alright, so our unknown is the parallel and the perpendicular components. So we just need to find FGX for my parallel and FGY for my perpendicular. Our equations. So we need to get theta first. So theta is just 90 minus phi. Not too bad. And then, of course, anytime we're breaking a vector into its components, we use the x component is going to be the length of the vector cosine theta. And for the y component, it's the length of the vector sine theta. Alright. Anything else I need to do? Yeah, probably. Remember, whenever we have Fg, we can always rewrite that as mg, and that's going to be our mass, 0.44, times the acceleration of gravity, which is 9.8. And so I always like to solve that before I get into the problem. So 0.44 times 9.8 equals 4.312. Alright, so now I can figure out over here My FGX is equal to 4.312 cosine. Oh, maybe I should do this first. Theta is equal to 90 minus 15 equals 75. So now that's 75 degrees. FGY is equal to 4.312 sine 75. So now, calculator time. 4.312 times trig cos 75 and 4.312 times trig sine 75. So on the top I got 1.116, 1.116. The bottom one I had 4.165. So I need to check my sig figs. I got 2 for my math, so that's what I'm going to use. That rounds this to 1.1 newtons. And this would be 4.2 newtons. Alright, so my FGX is going to be in the direction down the ramp. And my FGY will be perpendicular to the ramp. Instead of saying down, you could have also said parallel, and that would have been just peachy. Instead of saying perpendicular, you could have said 90 degrees into the ramp, and you would have gotten just fine. All right. Exercise 39. Stacy, who has a mass of 45 kilograms, starts down a slide that is inclined at an angle of 45 degrees with the horizontal. If the coefficient of kinetic friction between Stacy's shorts and the slide is 0.25, what is her acceleration? So let's write down some things. Givens, they gave us the mass. They said it's 45 kilograms. They gave us the coefficient of friction. It's 0.25. And they gave us our phi again. And phi is 45 degrees. Remember, phi is just that angle whenever we have the inclined plane problems. Alright, so time to draw a picture. Wow, what a pretty slide. It's at some angle. Okay. And then, just like before, we go straight down with my FG. We're going to come straight out at a 90-degree angle as my FN. And then we're going to go and make this, oops, for some reason. Try it again. If I could stop clicking the wrong thing, that'd be great. There we go. I'm going to come down straight like this, perpendicular, and then that one's going to be parallel to the ramp. Okay, so this is FG, which is equal to mg, which is equal to 485 times 9.8, which is equal to, go to the calculator, 45 times 9.8, enter, 441 newtons. Alright, this little component that I've drew in with the dots, that's FGY. This one right here is FGX. This is FN. And if we're traveling down the slide, that means we have one more force that we need to put on here. It means if we're going down the slide, friction is going to push us up the slide. And so we'll label that little guy F. The angle that we had was 45 degrees. So if you look at this, the picture didn't change. Every time we're doing an inclined plane problem, the picture is pretty much the same. And then we just go and solve. Okay, so my unknown is acceleration. The equations that we're going to use, of course, we're going to use theta is equal to phi, or 90 minus phi. We're going to use that FGX is equal to FG cos theta. We're going to use that FGY is equal to FG sine theta. We're going to use our reminder. These are really just definitions right here, but FGY and FN will cancel each other out, because otherwise we'd be falling through the ramp or we'd be jumping out of the ramp. So that's just saying that Fn is equal to FGY, which is really saying that Fn is the same thing as Fg sine theta. Then we have the force of friction, which is going to be mu times that Fn, which really means that, again, this is just a definition. The force of friction is going to be mu times Fg sine theta. And then we're going to finally get to F net equals ma. Alright, so our FGY and our FF or Fn are going to cancel. So the only forces that are left on my free body diagram is this force of friction and this FGX. So Newton's second law, that F net equals ma, is going to say that the force of friction, and if we're pretending like this is the x direction, it's going to the left, we're going to put a negative. We got FGX going the other way, so we got FGX is equal to our object's mass times our object's acceleration. So if I look here, my force of friction, we said all boiled down to right here. So I have negative mu times Fg sine theta plus my FGX, which is Fg cosine theta, is equal to the mass, which is 45, times the acceleration. Oh, sorry, I'm just going to write mass and then acceleration, and I'll plug all the numbers in. So I'm doing this a little bit differently, just showing you another option. In the other examples we've worked in class, we've plugged in all the numbers each time. This time I'm just plugging in the equations and then the numbers. It works exactly the same way. Alright, so now I'll write in negative, and mu was 0.25, times Fg was 441, times sine theta, 90 minus phi, 90 minus 45 is 45, plus Fg is 441 cosine 45 equals the mass, which was, oh man, making it easy, 45, times the acceleration. So we're looking right here. 45 multiplies times a. The opposite of multiplying is to divide this whole thing by 45. This means I can put all of this into my calculator at once. To do this correctly, you're going to want to make sure to use the magic fraction button. So hit Control Divide. And now we'll type in what's on the top. I've got negative 0.25 times 441 times trig sine 45. Close that parenthesis. Plus 441 trig cosine 45. Go down to the bottom and put 45. And then I hit enter. And we get the acceleration is 5.197. Our sig figs are only 2 of them. That means that we're going to round this to 5.2. So our acceleration is equal to 5.2 meters per second squared. We got a positive. Our positive direction was down the ramp. So we're going to say down the ramp. Or down the slide in this case. That's it for that. Oh man, I gave y'all another one. So we're probably starting to get pretty close on time in class. You know, we got another 10 minutes. But this is a good problem to look at, so it's good to look at this last one. Notice that this is not a problem where you're on ramps. 43 is a little bit complicated, but it's not that bad. So I'm going to start by reading the problem, then drawing a free body diagram, and then just adding up all of the forces. It says a large scoreboard is suspended from the ceiling of a sports arena by 10 strong cables. 6 of the cables make an angle of 8 degrees with the verticals, while the other 4 make an angle of 10 degrees. If the tension in each cable is 1,300 newtons, what is the scoreboard's mass? So, my free body diagram is going to look something like this. I have this object, and the object has a weight. This is my scoreboard. Fg equals mg, which is going to equal to the object's mass times 9.8. Okay. Now, there's some cables holding the scoreboard up. In fact, there are 6 of them that make an angle of 8 degrees with the vertical. Okay? So you should be thinking to yourself, it makes 8 degrees with the vertical, and we always measure theta from the positive x-axis. What angle is that going to be? Well, if I went all the way to the y-axis, that'd be 90 degrees, or the vertical axis, it's 90 degrees. This was 8 short of it. So that means that the theta for these, the 8-degree cables, is going to be equal to 90 minus 8, which is 82 degrees. Okay. The other ones make a angle of 10 degrees. So I'm going to draw them on the other side. 10 degrees with the vertical. So the theta for the 10-degree cables is going to be equal to, all right? So I went all the way to the vertical. That's 90. And then I went 10 more. Well, 90 and 10 is 100 degrees. Okay. So now I just need to break apart into components. So this is a little bit more complicated just because they added some extra stuff. So there are four forces, four identical forces right here. Ooh, not an equal sign. Four of these identical forces that are at the 10 degrees, but each force is 1,300 newtons. And on this other side, all of these are also 1,300 newtons. But there are 6 of them. Okay. So when I do my F net equals ma, my Newton's second law, all I have to do is multiply times 4 and multiply times 6, and I've got it all good to go. All right, so this thing does not care about anything in the x direction because we're only looking for Fg, which is mg, which is m times 9.8. So we're just going to solve F net equals ma in the y direction. Okay, and we're going to be solving unknown for m. So the other thing we have to think about is this thing is suspended from the ceiling. Hopefully it's not falling from the ceiling. If it's falling from the ceiling, we have a problem. So we're going to say that the acceleration is equal to 0. Our equation is going to be F net is equal to ma. And what we have going up, we have 1,300. Oof. Sorry. I should probably give you the equation for ay is equal to a sine theta. That's how do we get a y component of the force. So we got 1,300 times 4 sine, so we're doing these, 100 degrees. Okay. Then we have plus, because we're still going up on the other side, 1,300 times 6 sine of 82 degrees minus our Fg, which was mg, which was m times 9.8, equals m times a, which is 0. All right? I'm solving for m, so I got to get that on a side of its own. So I'm going to add 9.8 m to both sides. Okay, so I got 9.8 m over here on the right side, and I've got this whole ugly thing on the left side still. So before I rewrite it, since it's the only term on the left side, I'm just going to go ahead and put it in the calculator and simplify it. So 1,300 times 4 trig sine 100 close the parentheses plus 1,300 times 6 trig sine 82. Enter. Oof, 1280.45. So let's see, we got 12845 equals 9.8 m. All right, 9.8 is multiplying times m, so the opposite is to divide both sides by 9.8. Now remember, I don't like to round in the middle, so I'm just going to go back to the calculator. I've already got this number in here. Just hit divide by 9.8. And we get 1310. So the mass is equal to 1310 We come back up and check our sig figs. So we have 2 sig figs here, 2 sig figs here, 3 sig figs here. We're going to round to 2 sig figs. Means we're just going to stop this and say that it is 1,300 kilograms. That's our mass. Alrighty, so that is it for the review. Hope you enjoyed it. Putting it up on the YouTube in case you need to go back over it after class. I should be available for tutoring after school today. Anything else? Send me an email. Thanks, guys.